Okay, so let's get started on the first of today's worksheets. So this is 5.1 lecture worksheets. And this is those 5 major forms of energy that we see converting from one form to another. So there are the 2 major forms that I started talking about, which are kinetic energy and potential energy. You probably heard about that somewhere along the way. But broken down in a more practical sense, what you see daily that you can describe are these 5 major forms. So kinetic and potential is will cross over into these 5 major forms, but these are the forms that we see, okay? And so we saw some examples in that video, and then these in the worksheet are really examples that you do see, and we'll try to understand how the energy that you can see came from another form. So that's a conversion of one form of energy to another. And that's because of the law of conservation of energy. It is a law of the universe that states that there's a constant amount of energy, and energy is not created, energy is not destroyed, energy just converts from one form to the other. And sometimes it's in a form that you can't quite see, like the bonds in a molecule, and that's chemical energy. So that's the first is chemical energy is really not energy that you can see. It is usually coming from a chemical reaction. And so the standard chemical reaction that produces energy that you can see is a burning reaction, a combustion reaction. So burning, anytime you're burning something, that's called a combustion reaction. A combustion reaction is fire. It needs something to burn, that's the fuel, and it usually needs oxygen as well. So we looked at that for the combustion reactions of hydrocarbons. Oxygen is always a reactant. You have a hydrocarbon that's the fuel, and then the products were always carbon dioxide and water. But you get energy out of that, which is energy in the fire, that's light and heat, that's radiant energy, jumping down, and heat and light, that's any energy that radiates as a wave. And this includes all those electromagnetic forms of energy, not just heat and light, but you've got radio waves. You got anything that radiates as a wave. So the electrical energy is the flow of electrical charges, and that's electricity. Okay, and we will see the electrical energy coming from a storage source of batteries. So we will get in the example that I showed in the video, there was a light bulb that lit up from a battery. And so the battery is a stored source of charges, and the flow is a circuit that runs from the battery, one end of the battery to the other end, but through the electronic that you're trying to power with the battery, like a light or a phone. And so that's batteries have batteries are a stored source of energy. And when you basically turn it on, it runs the electrical current through your thing that you're turning on that's battery powered. So that's electrical energy when you have a flow of electrical charges. And so electricity can come from a battery. It can come from electricity in the house. When you plug something in, you turn on a switch, the same thing happens. You have a flow of electrical charges. Then there's mechanical energy. So mechanical energy is motion. So mechanical energy is something moving, like a fan or the wheels of a car. And it could also be due to position. So you could have mechanical energy that is due to something that's positioned on a high shelf, an object on a high shelf, like a book. And then once it starts moving, once it falls off that shelf, that's mechanical energy because it starts moving. And then you got nuclear energy. So nuclear energy is the rare one. It comes from inside of an atom, and we really don't see that in day-to-day processes. So this is specialized. As I mentioned, it's going to get its whole chapter, its own module. And so the ones that we see are actually 4 major forms: chemical, electrical, mechanical, and radiant. So let's look at these standard processes, day-to-day processes, like turning on a light. So turning on a desk lamp in your house. Well, you know that if you're turning something on, that's electricity, that's electrical energy. And what happens is you get this light. The light is a form of radiant energy. Okay, so it's a light wave that radiates. And so that's something to think about. When you turn on a light, the energy doesn't come from nothing. Energy is not just created in the light, it comes from the electricity, which is a flow of electrical charges. That's electrical energy. Water, when you have water in a dam that generates electricity, this is called hydroelectric power. And we'll talk about hydroelectric power in the next module because it is sustainable and renewable energy. But when water in a dam generates electricity, that energy is not coming from nowhere. So we get electricity. So we can definitely list what you get, the product, electrical energy. But where did the electrical energy come from? It came from the movement of the water through the generators that are set up in the dam. And so movement of water means that it came from this mechanical energy. Okay, mechanical energy is anytime you're talking about motion. How about when you're burning a candle? When you're burning a candle, you get light, you get heat from the flame. And that, anytime you have light and heat, you know that that is radiant energy. But where did it come from? Where did that light and heat come from? It didn't come from nowhere. It comes from the reaction of burning. And remember, burning is a chemical reaction, and chemical reactions mean that you're looking at the source, which was chemical energy. Anytime you have a chemical reaction like burning, that's chemical energy coming from breaking bonds, forming bonds in the chemical reaction. So that's chemical energy. How about cracking a glow stick? If you've ever seen one of those thin little plastic glow sticks, when you crack it, it actually makes a cracking sound. That's because you are literally cracking a thin little sleeve of glass inside of the plastic. And inside of that thin little sleeve of glass is a chemical reactant. And outside the sleeve of glass is a different chemical reactant. When you crack it, it causes those two reactants to mix. So when those two reactants mix, there's a release of light. And so that's why you actually have to crack it to get those two reactants to mix. And so what does that mean? So let's see. First of all, you know you get light. So you know on the other end is radiant energy, because light is energy that radiates as a wave. But where did it come from? So it didn't come from nowhere. It came from the chemical reaction of those two reactants. And so a chemical reaction is chemical energy. How about the process of burning a wood splint? So anytime you're talking about burning, that's a chemical reaction. That's a combustion reaction. So that's a chemical reaction, meaning that there's chemical energy. Bonds are broken and new bonds are formed. So that chemical energy is converted in the combustion reaction, in the burning process, it's converted into light and heat. That's radiant energy. Okay. How about photosynthesis by plants? So plants do great things. Plants provide us with food. Plants convert carbon dioxide into oxygen. And this is the process of photosynthesis. So what do plants do? They take the energy from the sun and they convert it into energy for, basically the plants are just trying to continue their life or their growth. And so first, let's talk about the photosynthesis, taking energy from the sun. What is that energy from the sun? Energy from the sun is it chemical, electrical, mechanical, radiant? Well, what we get from the sun is light. And so light from the sun is radiant energy. Okay, so plants take that visible light and they turn it into, convert it into chemical energy. Okay, this is chemical energy that's stored in the compounds that plants make. So plants make or they convert carbon dioxide into oxygen. Those are bonds that are broken and new bonds formed. They also form their own nutrients. So plants form nutrients that then we take advantage of. Corn, that's the fruit of the plant, or the leaves themselves. And so that's chemical energy that's provided by the breaking bonds that originally came from the sun. Okay, how about when you drive a car that is powered by gasoline? So first of all, we know that the gasoline is being burned in a combustion reaction. So when you have a combustion reaction, that's chemical energy. There are bonds broken and new bonds formed. And so the combustion of a hydrocarbon like gasoline produces a lot of energy. And that's why we'll get into that in this chapter. But the energy that we get out of the combustion of gasoline, well, you get the movement of the car. So when the car moves around, the energy of motion is mechanical energy. You also get, when you are driving a gasoline powered car, if you've ever noticed, the engine gets hot. So you also get some heat. And what kind of energy is heat? That is, heat is part of the radiant energy. Okay, so you get mechanical energy and radiant energy out of the original chemical energy from breaking the bonds of gasoline in the combustion reaction. Now, it's a little different if you're driving an electric car. So an electric car, where does that come from? Where does the energy come from? Well, this comes from electricity, right? And so that original electricity, which is electrical energy, might be from plugging it in. It might be from plugging in and charging a battery. But either way, the battery is just a stored version of the flow of charges that then powers the drivetrain of the electric car. So when you drive that car, it converts that stored electrical energy into energy of motion. That's mechanical energy. And the nice thing about driving an electric car is it's not a chemical reaction. It's not a combustion reaction. So you don't actually have any heat. And so that's why if anyone does have an electric car, these electric cars do not waste energy in heat that's lost to the environment. And so that's the nice thing about electric cars. They're quiet because it's not a chemical reaction. Basically, why is a combustion engine kind of loud? It's because there are a bunch of little explosions in there. And so an electrical car does not have a bunch of little explosions. That's why it's quiet. And it also doesn't get hot. Okay, we're also going to talk about how electricity is generated in a coal-fired power plant. We've seen coal-fired power plants before. That was way back in module 2 because we talked about air pollutants that originate from coal-fired power plants. Sulfur dioxide is the main air pollutant that comes from a coal-fired power plant, and that's because coal has these little bits of other atoms in there. Coal is a hydrocarbon that also has a little bit of sulfur, a little bit of nitrogen, a little bit of mercury. And when you burn coal to generate electricity, or when you burn coal in a factory to generate electricity for the factory, you get those air pollutants as side reactions. So what happens in a coal-fired power plant to generate electricity? Well, the first thing is you are burning coal. So you are burning coal, and this is combustion of a fossil fuel. And so in the process of burning coal, this generates heat. Okay, and so that's radiant energy. You get heat and light, but the main purpose of burning coal in a coal-fired power plant or in a factory or in a home is to get heat, okay? And so that heat is radiant energy. And so that heat is then used to boil water. That's it. Burning coal, burning that fossil fuel, combustion reaction of a fossil fuel is just so you can get hot enough so you can boil a whole bunch of water. Okay, and then that water becomes steam. And you guys have hopefully seen that process. When you heat up water hot enough, it turns into the gas form, which is steam when it's come from the process of boiling from heat. Okay, so this is water vapor. And that water vapor is a gas that moves through the system. So this water vapor, the steam, moves through a series of pipes. Okay, so this steam moves, it flows. And what it does as it flows is it moves through a generator. Actually, let me put this on this side of the arrow. Moves through a generator. And this generator basically is like a fan. Instead of the fan being plugged in and the fan blades moving because of electricity, what the steam does is it moves through the fan and it causes the blades to move. Okay, if you've ever done that, like if you've blown on a pinwheel, you can blow or generate movement by pushing a gas or air through some blades. Okay, and when it moves through a generator, it causes this generator is connected to some magnets will generate electrical energy. And so that's electricity, and that's electrical energy. So when you have the steam moving through and moving these blades, it's connected to a generator that has these magnets attached to it. And because of the magnets and motion of the magnets, you'll get electricity generated from that. And so that is the process. That's how electricity is generated. And one thing to point out in this process is this part. Why the coal is being burned in the first place is to get some heat. And that's what's interesting, is when you really understand how electricity is generated, what you need to do is just replace this part. We can get heat from other sources. And so that's what we'll be getting to. But we'll also look at a schematic of a coal-fired power plant. And you also have this as part of your questions for your Quizlet today. So let me see if there's any questions. This one at a time. So the first major fossil fuel energy source is coal. And so these are coal-fired power plants. This is to generate electricity for the grid or to generate electricity for a factory, like a factory that makes steel in the US, in Pennsylvania, or a factory that makes iPhones in China. Coal is typically the main energy source for those types of factories. And so what are the energy conversions in a nutshell that we looked at in the last is that coal is a chemical reaction. And so that's chemical energy. And you get chemical energy from the combustion, from the burning of coal. And then this chemical energy becomes heat. That's radiant energy. And that's radiant energy, that's heat that's used to boil water. And when water moves, it's mechanical energy. So water becomes steam that moves, to be specific, and that's mechanical energy. And when that steam moves through a turbine that's connected to a generator, you'll get electricity generated. So that's how we get electrical energy. That's how we get electricity for the grid. That's where your electricity is probably coming from right now. So there are many drawbacks of coal. Number one is carbon dioxide emissions. For all the countries that have signed on to the Paris Agreement, carbon dioxide emissions have got to be cut by 2030 and 2050 are the deadlines. And so we can't be using coal if we're going to be trying to reduce carbon dioxide emissions. And so that's number one, because carbon dioxide emissions are leading to our climate change issues. It's also very inefficient. This whole series of reactions, let me add this in a different color. This is inefficient. I mentioned that in the video, is that there's a loss of heat to the system, to the surroundings, to the plant itself. The whole place is hot. And that's a waste. So it's less than 50% of the energy that you put into it is what you get out of it. And that's a waste. Now, almost every single one of the energy sources that we have is inefficient, but it's just a matter of how inefficient. Okay. So it's inefficient if it's in a coal-fired power plant. It's also inefficient, as I mentioned, for a gasoline combustion engine car. All that heat is just wasted in an engine when you have this gasoline engine. And so you don't get to use that heat. It's just lost to the surroundings. Okay, so you have that as a kind of side drawback. They are all going to be inefficient reactions to some degree, though. Okay, so you also have things emitted are air pollutants. Coal is special because you get the air pollutants, you get all of the air pollutants. You have sulfur dioxide, you have nitrogen dioxide, you have soot, that's particulate matter, PM. You have some carbon monoxide, and you also have mercury, Hg. They all originate from coal because coal is this carbon reservoir. It's hydrocarbons that over 65 million years have been basically compressed into a little solid, which is a lot of bonds in there. And then a few other things got trapped in there. So there's different types of coal. Some are cleaner than the others, but no matter what, that's all 65 million years worth of stuff that's stuck together, and you're going to get some mercury in there. You're going to get some other things in there that are going to end up burning in the combustion reaction. Then finally, the underground mining of coal is dangerous, as well as the mountaintop removal mining of coal. So it used to be that you dig down underground, you go down underground with your shovel and get coal. Well, now in lots of countries, they just shave off the top of the mountain. That's called mountaintop removal. And this is done in Appalachia in the US. So that's Tennessee, Kentucky, West Virginia. They just cut off the entire top of the mountain so they can dig out easily with giant diggers the coal that they want. Well, then that leads to what I showed you is runoff, and down the side of a mountain in Knoxville, Tennessee, a whole city was engulfed by this unstable mountain coal sludge. So that's dangerous to the people around. Coal mining is dangerous for the people who have to go in. And there's cave-ins, there's explosions, there's poisonous gases, long-term respiratory diseases. I don't think any of us actually aspires to be a coal miner for all those reasons. It's just doesn't sound fun either. So there's environmental harm of mining that is something that is basically any town that's a mining town has issues, whether you're digging underground or taking the top of the mountain off. So lots of issues with coal, and there has been lots of pushback about coal. And so we'll look at the other main sources of energy next. Let me check if there's any questions. Oil. So the energy conversions of oil are basically the exact same as burning the fossil fuel of coal. Oil is also a fossil fuel. It is meant to be in the carbon reservoirs, but we pump it out from underground, and we pump it out because it is chemical energy that can be burned in a combustion reaction to generate heat. Heat is radiant energy that is then used to boil water and turn it into steam, and then that steam can move. That's mechanical energy when the steam moves, and it moves through a turbine that is connected to a generator, and that generates electrical energy for the grid. It's the same exact process. As I mentioned, the whole goal is to get heat. And so that's from a combustion reaction for all three of these fossil fuel energy sources. So what were the drawbacks? So the drawbacks are that this is still inefficient. It's still inefficient because of the loss of heat that happens when you are basically boiling this water. Some of the heat is used to boil, most of it, but then some of it is just lost in the whole system. And so that is not a heat that can be captured. And so this is inefficient, but a little less inefficient. Instead of 50%, it's more like 60% energy that's captured from the bonds, the chemical energy. So the main drawback is carbon dioxide emissions. Remember, we're trying to cut carbon dioxide emissions. So this is, though, with oil, it is not like coal. So coal has those other air pollutants that are side reactions because coal has those other atoms in there, the sulfur, the nitrogen. Well, oil is only a hydrocarbon, so it does not have those other air pollutants, and that's why it's called clean energy. Okay, it does not have that. It still has the carbon dioxide emissions, which is something we're trying to get rid of. The other thing I mentioned is that refining requires energy. So refining the petroleum or the oil that's dug out, that is pumped up from underground, requires energy. And let's just dumb, okay? If we're going to get energy, why should we need energy to get energy? So that's just a waste. And the refining goes back to pumping of oil. Well, that is something that is a problem. Right now, there's an oil spill off the coast of Huntington Beach and Laguna Beach, threatened because of an oil spill. They believe that it was an anchor dropped into an ocean pumping system that then broke a pipeline. And so now there's a whole bunch of oil in the bay right off of the shores outside of Santa Monica. And this is pumping oil leads to oil spills. And that's environmental. That's an environmental cost. So it's environmental harm to the beaches, to people who want to use the beaches, but how about all the marine life that don't even realize what's going on around them? And then finally, there's peak oil. The bottom line is we're going to be out of it. There are reserves of oil all around the world, and for that reason, wars have been fought over the oil reserves, say in Saudi Arabia, compared to Kuwait. And so this is all underground, and there's all of this oil that are in reserves underground. We're not going to have those. And so peak oil is something that is real, and it is why we will talk about in the next module. The main use of oil is basically it is refined into gasoline, and it is why gasoline powered cars are being phased out. The electric car is a thing, so we'll be getting to that too. But right now, let's get back to our worksheet, and this is the last fossil fuel is natural gas. So that's also methane, and it is also meant to be a carbon reservoir. So natural gas has to be pumped up from underground, just as coal has to be dug up from underground and oil has to be pumped up from underground. And it is the same fossil fuel reaction where you start with burning the combustion of the methane. So methane is a hydrocarbon, and that is a combustion of a hydrocarbon. And the purpose of burning it is to get heat. So heat is radiant energy. And that radiant energy is used to boil water. So that heat is used to boil water, and that is mechanical energy when the water becomes steam and moves through the system. So that steam moves through a system that then moves the turbine blades that are connected to a generator, and that generates electricity or electrical energy. So this is just like the others. It is inefficient. Anytime you are trying to boil something and boil water and get heat by burning, that is going to be inefficient. You're going to lose heat you're going to lose that radiant energy to the surroundings. And so that's why this theme we'll get into renewable energy does not necessarily have to have the combustion reaction. So let me write that down here, is that combustion reactions overall, these are the burning of fossil fuels. These are all inefficient. These are fossil fuels. These are all inefficient because the burning, the fire will lose heat to the atmosphere, heat or energy, radiant energy to the surroundings. Okay, so what we get out of natural gas is that we know that it's the same carbon dioxide emissions. When you burn a hydrocarbon, you use oxygen as a reactant and you get carbon dioxide and water. So carbon dioxide is an emission, and we need to lower those carbon dioxide emissions. So we're going to have to somehow replace coal, oil, and natural gas if we are going to reduce our carbon dioxide emissions by 2030 and 2050. So this is the natural gas is a gas, and it is a gas that is unstable to transport. So moving natural gas around, whether it's in a pipeline or in a big truck, natural gas is unstable and very explosive. And that is different from coal and oil or petroleum, which is a liquid. So coal is a solid and oil is a liquid. Those are not as unstable to transport as gas. Being in the gas form, natural gas is very explosive. And so we've seen that natural gas is also invisible. And so when there have been natural gas leaks, like here in LA, we've had natural gas leaks in a neighborhood called Porter Ranch. That can cause a local explosion unknowingly because it is not something, it's invisible. And so this is unstable to transport. And we also know that fracking is being used to access the remaining stores of natural gas that are underground. And fracking requires energy. That's one issue. Just as refining of oil requires energy, and that's kind of dumb. Why does our energy source need energy? Same thing with fracking. Fracking requires energy. You need to pump hot water down in order to get the gas coming out, the remaining stores of gas. And so you also need to fracture the underground shale. That takes energy. And that's why hydraulic fracturing, that's what it's called, is you are breaking this underground shale using hot water. And that takes energy. So that's a waste of energy. It's also a waste of water. And it's just stupid. Why should your energy source need energy? And this leads to also water contamination. So the water that is pumped underground in the fracking process will then seep into and contaminate nearby underground water. And that's water in aquifers, stored water that we drink. And then there are also seismic events. Seismic events from fracking really led to the banning of fracking in certain states and countries. So there's the major fracking that goes on in the US is actually in Oklahoma, which is basically leading to earthquakes in Oklahoma, where there should not be earthquakes in Oklahoma because there's no fault line, but there are daily earthquakes in Oklahoma, low, less than 3 on the Richter scale, but it's all human generated, and it's because of fracking. So this is something to think about, which is all of these, the burning of fossil fuels are inefficient. And they are also contributing carbon dioxide, which we can't have. So we move on to talk about sustainable energy sources, because we do need electricity. We do need electricity for the grid. We need electricity for factories that make stuff. And we need to start talking and moving towards renewable and sustainable energy sources. Okay, so let's get to solar energy. Solar power has the greatest potential to currently and even long-term replace all those coal-fired power plants. It does have some drawbacks, but it right now is considered the greatest potential to replace, to basically get it done. We need to cut those carbon dioxide emissions, and we also need electricity. Where is it going to come from? Well, sun is free. It goes to all countries. We need a few things though. So let's first get into, this is the energy conversions for solar power. There were two. So you either have solar thermal, which is taking the energy from the sun. That's radiant energy. And that will be used to heat up water. So that's the same process. It actually is a good starting point. It's the same process. When you're just heating up water, you're taking water and getting it to boil. And we do have a nearby solar thermal plant east of LA, about 3 hours, but it basically is just taking water and taking water in pipes where mirrors are used to focus solar light and the heat energy, and boil water. And when you boil water, that will turn water into steam, move the turbine, and generate electrical energy in the process. Sorry, I got to sneak that in there. Can I move this over? No, I got to sneak that in there. Sorry. So that's the solar thermal process. But what is different is we'll move into just the standard solar array. This is photovoltaic cells that don't heat up water. And so that is a straight up conversion of radiant energy into electrical energy. And it doesn't have the middle step where you're boiling water. And the conversion is not as great. It's less than 50%, it's 20% about. But there's the energy that's wasted is not actually energy that's wasted. So it's because we are getting the energy from sun. So that's a kind of a nice thing. I don't even think it should be considered wasted, but it does mean that science is working on having the conversion of energy to be more efficient in those photovoltaic cells. So it is inefficient in the fact that we could get a lot more energy from the sun if it were 100% conversion of that energy. And that's going to have to be done at the materials science and chemistry level of the conversion inside of the photovoltaic cell. Okay, so some drawbacks are you need sun. So you need sun, and you need land, and you need photovoltaic cells. You need those solar panels. Okay, so all of that, well, the sun, let's first talk about the sun. As I mentioned, you have to have a certain area, regions, and certain regions of the US or whatever country you're in get more sun than others. So you need to have land that is sunny, and you also need to give up that land. Now, if the US energy needs would require about a state the size of New Jersey, which we do have, we might have to like move some people out of the way that are in the southwestern United States, but it can be done. This does not happen on every country. Not every country has plenty of sun, but we do here. The space and sun, also you need a startup cost of all those solar panels. They're not cheap. And so that's why the startup cost for oil and coal and methane and natural gas, that was taken care of at the beginning of the century. But right now we have a startup cost for solar, setting up solar. And that is not only the panels expensive to produce, but setting up all the solar arrays, the land that's needed, that's going to happen. Okay. We also know that these solar panels, these photovoltaic cells, require rare metals. And those are rare metals that have to be mined. Just as I mentioned in the very first day of lecture, when you're talking about a smartphone, there are rare metals in a smartphone. Those have to be mined. And there's an environmental cost when you are mining rare metals. And so whether it's for a smartphone or for the arsenic and gallium, those are very rare metals that are needed for a solar panel, there is an environmental cost there. You also have this, but it has this great potential. So you can use it off grid. You can have like the little solar panel. Other countries that are not on the grid, let's say you have countries that are not completely, have a grid at all, namely developing countries, can use a small solar panel to power, let's say, a water pump or just a single house or single region. And one great thing is that there are no emissions. So this is not a drawback. This is a good thing. There's no carbon dioxide emissions from this solar power. Okay. There might be in the processing and making photovoltaic cells and mining metals, but this is what we're trying to get to. No carbon dioxide emissions. And also there's no air pollutants because it's not a chemical reaction, right? So that has the greatest potential to currently and even long-term replace all of the coal-fired power plants around the world. It just has to happen. So there's going to be some startup costs involved. So there's startup costs, there's startup requirements, and this will be every country in the world needing to do this. So let's take a pause here. Let's add on for the wind, hydroelectric, and geothermal, and we will get to nuclear power next time. So save this worksheet, but let's look at the wind power. So the energy conversions of wind power are, you take the wind, which is moving, that's mechanical energy. And that mechanical energy is directly used to move the turbine blades and generate electricity for the grid. So you don't have to heat up any water. There's no chemical reaction. And so this also, I'm going to make this in red actually, also has no carbon dioxide emissions. When you're not talking about burning a fossil fuel, when you're not talking about a combustion reaction, you don't have that issue of carbon dioxide emissions. There were some drawbacks of the wind power. So there's the startup costs. Then there's also maintenance. So unlike solar panels that really don't have to be maintained, when you're running a wind farm, you have got to set up these moving parts. You got to set up these windmills and they're moving. And that's actually an interesting job that I read about recently, is that it's a combination of kind of a daredevil that goes up there to repair the fan blades on a wind turbine generator. Those fan blades are way up there, usually like hundreds of feet or several stories, like 10 stories high, 100 feet. And that's significant. So there's startup, there's maintenance, there's requirements. You also need land. Okay, so that could be considered an environmental cost. Just as the solar arrays need land, you need a whole bunch of space for all those windmills. And there's a small consideration of birds that don't realize and fly into these wind farms. And that is an issue, can be an issue as well. But it is used in conjunction with solar. So if you can put some windmills around your solar arrays, you're kind of taking advantage of when it's not sunny, it's windier. When it's windy. When it's not windy, it's sunny. And that's a good use of land. So it can also work on the micro scale, as I mentioned, and all countries have some wind. So especially offshore. So there's offshore winds naturally here, even in California, and this can be very promising for island countries that are really small and want to generate electricity. Well, they generally have lots of wind being an island and having offshore winds. So this is promising, but really not used enough, Hydroelectric. So hydroelectric, let's talk about that one. Hydroelectric is basically like wind power, except for it's water power. So you have water that's moving, and this harnesses the movement of the water. That's mechanical energy, and it directly turns it into electrical energy. So instead of boiling water, you just take water that's already moving. And so for hundreds of years, humans have done this, used hydroelectric power to generate energy, but it wasn't always electrical energy. It was to grind grain that I showed you in the video. So this is sustainable, it's renewable, there's no carbon dioxide emissions because it's not a reaction. There's no pollutants, but you need a river. So not all countries have a big river. And so there can be an environmental cost from damming up a river. Because there are fish in the river, and what happens to the fish when it meets this dam? Well, it's not going to end up where it needs to go. And there's the infrastructure cost. So there's also startup and maintenance costs of building a dam in the first place. So building and maintaining the Hoover Dam is not insignificant, but it is something that I highly recommend if you guys go that direction. If you go out to Las Vegas, take a stop at the Hoover Dam and take the tours there. It's a great example of hydroelectric power, and in fact powers quite a bit. I think it was up to 20% of the region's power needs. And so this is last one, geothermal. So geothermal, harnessing heat from Earth, the core. So we do need, geothermal means earth heat. And this is basically taking that heat, which is radiant energy, and this time boiling water using that radiant energy without a reaction. So this is the same back half where you have water that's being boiled into steam, mechanical energy that moves the turbine blades, and that's how you get electricity for the grid. But again, there are no carbon dioxide emissions because it is not a chemical reaction. It's just taking the energy, the Earth's heat. And so there are some drawbacks. One that is that it's location based. You need geothermal activity in the first place. So you need a natural hot springs. Or that usually means a volcano. What we have in the US is Montana and Colorado. There are some hot springs. We also have some in California, but you're not going to drill all the way down to the core of the earth. You're going to drill to some hot springs, some hot water that is hot because it's heated from the core of the earth. You're going to drill down into those hot reservoirs of heat that are hot springs on volcanic activity that is usually going to have hot springs near, and that's usually and here it's in the Western US. And so we have that location-based, which not all countries have, okay? So there's also startup and maintenance costs, but mostly the startup costs of drilling down in the first place. And the US, though, as I mentioned, currently leads the world in this geothermal electricity generation, but other countries have gotten on the bandwagon, and that's great. So that we will leave nuclear power for next time, okay? But that, I see now that I went over, sorry. Hopefully you guys are able to get all that, and I will post all this when I finish recording.